All right, welcome back, everybody. So today is the second lecture in our series on ordinary differential equations. Remember, ordinary differential equations, we call them ODEs, have the form y dot equals f of y. So y is some vector of states that I care about. F is perhaps a nonlinear function that operates on this vector of states. And dot means time derivative. Okay, so the time derivative of my state is equal to some function of my state, right? Most physical systems can actually be written in this form. And so it's very, very useful for lots of applications. Okay, so recall that last time we introduced the forward Euler method of integrating. So what we really want to do is we want to start with some initial data. I'm going to say y at time 0 equals y0. This is just an initial condition to my system. And what I want to do is I want to come up with a rule for how I integrate this trajectory forward in time along my dynamical system or my differential equation. Okay? So I might sometimes call this a dynamical system, and we call it dynamical instead of static because there's this time-varying nature. Okay? So the forward Euler equation, we say yk plus 1, y at time k plus 1, is equal to yk, this is my previous point in the trajectory, plus delta t times f of yk. Okay, so yk was the last point in my trajectory. Delta t is how much farther in time I'm moving forward, and yk plus 1 is my next point in time. So there's often some confusion about what these indices really mean, this underscore k and underscore k plus 1, so I want to be very explicit. So what we have is that yk plus 1 is equal to y at time t k plus 1. Okay, so I have time increasing, and I want to know what is the next position in my trajectory. But it's not actually exactly equal to this. It's only approximately equal. So the way I think about this is that the state y might be an actual physical object. Maybe it's an asteroid or a comet moving through the solar system, and it has a real position at every moment in time. And what we would like to do with our numerical scheme is approximate the true position at time tk plus 1, where time tk plus 1 is just time tk plus delta t. So every time I move my index 1 forward, I'm trying to find my particle position, the position of my state, at delta t further in time. Okay, so the way I like to draw this is I have some trajectory with a number of points. Okay, maybe this is y0, my initial data, y1, dot, 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 and all the way up here I have yk. And what this forward Euler scheme and really all numerical integration schemes do is they give me a rule for predicting where this particle will be at the next moment in time. So if I put some axes on here, we can say that this is the time axis, and all of these trajectory points are spaced delta t apart, right? This is tk, and this is y. Okay, so that's what these indices really mean, and this is the rule, the forward Euler rule, for constructing a trajectory, right? We start with y0, we get y1. We plug y1 in, we get y2, then we get y3, and so on and so forth until we built up our entire trajectory. Okay? All right, so this is what we did last time, and now what we would really like to do is start to assess how accurate this method really is. Okay, so I told you that there are much more accurate methods that exist, such as the Runge-Kutta schemes, and I actually told you that the implicit Euler was often more stable. So what we're going to do is we're going to start looking at and assessing the stability of this numerical scheme. Okay? All right, so let's think about, first of all, just the error properties. Okay, so we're going to look at error properties. And just like we did when we were doing numerical differentiation and integration of data, we're going to look at the Taylor expansion, okay? So we're going to look at our exact trajectory. We have y at time tk plus delta t. This is my exact trajectory, okay? And we're going to Taylor expand this about the point tk in time. Okay, so this equals y at tk plus delta t times dy dt evaluated at time tk plus higher order terms, right? This is a infinite expansion. There's second derivatives, third derivatives, and so on. And I'm going to wrap those all up in this term delta t squared over 2 factorial d squared y dt squared evaluated at some constant c, where c is between tk and tk plus 1. Okay, the way that I do this is using the mean value theorem. I'll just sketch that in a minute. But I really want to just write out explicitly that this is equal to yk, right? Y at time tk, we think that's yk, plus delta t times dy dt evaluated at tk. This is the same as, right, dy dt on the other board is just y dot. So it's equal to f of y. Okay, so here we plug in f of yk plus order delta t squared. Okay, so this is the Taylor expansion of our exact trajectory about the point yk, or about the time tk actually. And we see that we have exactly our forward Euler plus an error term, which is order delta t squared. Okay, and this delta t squared error term, that really means that our local error, we're going to call this epsilon k plus 1, is equal to our exact trajectory minus our forward Euler trajectory, right? This is y tk plus delta t minus yk plus 1. This is exact, and this is our forward Euler approximation. And this is exactly equal to delta t squared over 2 times the second derivative in y with respect to time evaluated at this constant c. Okay, so the local error is order delta t squared, which means every time I take a time step, that time step is giving me an additional order delta t squared error. Okay. Now I want to just clarify how I got this constant, because we're often used to writing plus higher order terms or plus order delta t squared. And so I just want to give you a really quick idea for why we have this constant. This boils down to the mean value theorem, and if you have interest, you can look at the little supplemental 5-minute lecture on the mean value theorem. But what the mean value theorem states is that if I have some function of a variable x, okay, so f versus x, let's just make a nice well-behaved function. And I have it defined between points, xk, maybe I'll have this be a function of y, since I'm using y as my variable. And it's defined between yk and yk plus 1. Okay, so what the mean value theorem states is that, so there's a line that goes between these two data points, this line here. The mean value theorem states that there is some intermediate point c between yk and yk plus 1, where the function derivative is the same as the slope between these points. Okay, and if you work out, just work out the math of what that means, and you'll find that you can exactly remove these higher order error terms. So that's all I'm going to say for now. There's a 5-minute supplemental video where we're going to actually work out all of the algebra to show that what you can do is actually remove the higher order error terms on the left board and obtain an expression in terms of a second derivative of a constant. Okay? Okay, great. So we had a local error term. On the left board, we had this local error term that every time step from k to k plus 1, we accumulate this error, which is order delta t squared. But we're not interested in taking one tiny little time step for our trajectory, right? We want to know, where is my asteroid going to be 5 years from now, right? Like, we actually actively are keeping track of as many large objects in the solar system as we can, and we'd like to know with some accuracy where they are as far in the future as we can. Okay, we have a very important stake in this problem. And so we're not actually always interested in the local error, but often in the global error. Okay, now different people have different words for what I'm talking about here. I like to think of it as local error at every time step. And then the global error is, as I take a number of time steps, how does my error accrue? And maybe I'll just pose this as a question to the class. So how do you think that this global error is going to accrue? Right? Let's say I'm not trying to integrate a little delta t. I'm trying to integrate 5 seconds into the future. How is my global error going to scale? Well, I guess what you do, very similar to how we drew it before, right? We have time, a bunch of delta t's, and our trajectory is going through here. And so we need to take as many time steps as there are t over delta t. Okay, so we're going to be taking a number of time steps, and each of them is going to have this local error. So if I write down my global error, big E, k, is equal to the sum from j equals 0 to k of my little epsilon k. Okay? Maybe instead of t here, we can just call this from point A to B. So then my time is b minus a, and I'm taking b minus a over delta t number of steps. Okay? In this case, I take 1, 2, 3, 4 steps to get from A to B. Okay, so this is equal to b minus a over delta t times delta t squared over 2 d squared y dt squared at some constant. And if we follow this all the way through, we get b minus a over 2 delta t times the second derivative. So our global error scales like order delta t, and our local error scales like order delta t squared. Okay? So what this means is that if I want to integrate a trajectory for some amount of time from A to B, I'm going to have order error on the order of the time step that I take. And remember, this is not a very good error scaling, right? That means to get small error, I have to take a very, very, very small delta t, which means I have a lot of time steps in between. Okay? Okay, good. So that is just kind of an introduction to how we compute the error properties of a numerical integration scheme. You can do the exact same procedure for backward Euler, and you'll find that it has similar error properties. Okay, so neither of these integrators are very accurate. Okay, in addition to looking at the error properties, kind of how much error accumulates at every delta t, we also want to look at the stability properties. Okay, so we want to know, for example, if I'm simulating some mechanical system, like in the last lecture we had the system where I had a mass attached to a spring attached to a wall. And if I pull the mass and let it go, it oscillates back and forth and eventually dies out. So it was a stable system. Okay? And what we're interested now is, does our numerical integration scheme preserve the stability of our system, or could our numerical integration scheme actually make our predictions go unstable, which would be incorrect? Okay? So now we talked about error properties. Now we're going to talk about stability. And stability is a very important idea, much more general than what we're going to talk about in this class. Very, very important property, and it's related to what we discussed about eigenvalues and eigenvectors before. So I like to start out with a really simple example that is a one-dimensional ODE. Okay, so my first example is I have y dot equals lambda y, and I have y at time 0 equals y naught. Excuse me. So this system, we're going to say that y is not a vector, it's just a number, right? A scalar y. This is a linear first order differential equation with initial conditions. I can actually write down the solution, right? I can say, well, we know the exact solution is y at time t equals e to the lambda t times y naught. So this is my exact solution, okay? But we want to know if our numerical integration scheme preserves the stability of the system, okay? So what I'm going to do is I'm going to write down the forward Euler, and I'm going to write down the backward Euler, and then we're going to look at when they are or are not stable. So this system, for example, is, we would say this is stable if lambda, if the real part of lambda is less than 0. Okay, so for example, if this is y dot equals negative y, or y dot equals negative 10y, then that's going to be stable because e to the negative 10 times some time gets really, really, really small, and this shrinks to 0. Okay? But we are interested in the numerical stability of our scheme. We want to know, do we track the true solution accurately? Okay, so in the case of forward Euler, and I'm just rewriting this from the previous board, we have y at time k plus 1 equals, I'm going to write it this way, 1 plus lambda delta t times y at time k. Okay, so this is exactly the same. We say y k plus 1 equals yk plus delta t times f of yk, which is lambda yk. Okay, so you can convince yourself that this is exactly the forward Euler scheme. And backward Euler similarly. Is yk plus 1 equals, okay, now we have 1 minus lambda delta t inverse evaluated at yk. Okay, so this is just what we derived in the previous lecture regarding forward Euler and backward Euler for a linear system. And we've made the additional assumption that instead of a matrix set of equations, y dot equals ay, we now have a single linear equation, and it becomes this simple. So how do I know what the stability of a system is that looks like yk plus 1 equals some a, some number, times yk? This could be a matrix or a number, but here it's a number. Remember, how do I tell the stability of this, this iteration? How do I know if yk plus 1 is going to get bigger or smaller, or what's going to happen? That's right. I look at the eigenvalues of A, or in this case, because this is just a number, the only eigenvalue is that number. Okay, so this and this, I look at the eigenvalues of those numbers, and it's just those numbers. Okay, so if these numbers are outside the unit circle, then the system's unstable. And if they're inside the unit circle in the complex plane, then it's stable. This is what we've learned from eigenvalues and eigenvectors. We used this before when we were looking at iterative solutions. This is a very, very important concept, that this numerical iteration will be stable. Let me just write this down because it's so important. This will be stable if all of the eigs of A are inside unit circle, and unstable if even a single eigenvalue is outside the unit circle. Okay. And when I say unit circle, of course I mean the unit circle in the complex plane. Okay, so being inside the unit circle is good, being outside the unit circle is bad, but for this simple example with a scalar vector field that's linear, the only eigenvalue is just this number, 1 plus lambda delta t, or 1 over 1 minus lambda delta t. Those are the eigenvalues, okay? So let's write out what this looks like on the next board. Okay, so what we're going to do is plot in the complex plane what types of lambda delta t's will give a stable system and what kinds will give an unstable system. Okay? Okay, good. So I like to just think of this pictorially. In my forward Euler scheme, I have a trajectory y0 goes to y1, goes to y2, dot, 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 goes to yn. And in this case, we can write down exactly what yn equals because our system is so simple, right? So yn equals 1 plus lambda delta t to the n power times y naught. Now, lambda can be a complex number in general. There's no reason I can't have a differential equation with a complex coefficient. It sounds weird, but you can have it. And so this expression is unstable when the modulus, or the length of this complex number, is bigger than 1. So when the absolute value of 1 plus lambda delta t is bigger than 1. So let's say, for example, lambda is minus 100, really stable linear system. Lambda is minus 100, and delta t is 0.1. So minus 100 times 0.1 is minus 10, and 1 minus 10 is negative 9, and the absolute value of negative 9 is 9. So this magnitude will become 9, then 81, then 81 times 9 times 9 times 9. It's going to get bigger and bigger and bigger, and this will be unstable, even though our lambda was very negative, and the system should, in fact, be quite stable. Okay, so this is unstable when. Similarly, I can write down my backward Euler scheme. I'm going to say backward Euler is y0 to y1 to dot, 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 to yn, where for backward Euler, I have yn equals, any guesses for what yn equals? Well, it's going to equal 1 over 1 minus lambda delta t to the power n times y naught. And again, we see that this is unstable when the magnitude of this object is greater than 1. Okay, so when the absolute value of 1 over 1 minus lambda delta t is greater than 1. Okay? Maybe I'll just label this. So here we have, this is the forward Euler stability, Fe, and this is the backward Euler stability. Okay? So let's look at what this means in the complex plane. Okay, so now remember the stability of our true differential equation on this right board here, y dot equals lambda y, this only depends on lambda, right? For the true system, think of this as an asteroid or whatever you like, some particle that's doing something. The stability of this system only depends on lambda. If lambda is negative, if the real part of lambda is negative, this will be stable. If the real part's positive, it will be unstable. Okay? But over here, our numerical scheme actually depends on lambda times delta t. Okay, so it doesn't suffice just for my true system to be stable. If I choose delta t poorly, my system, my numerical iteration might in fact be unstable. Okay, so this is kind of a cool picture that people like to draw. If you are an aerospace engineer, you may have seen plots like this before in the complex plane. So what we're going to do is we're going to say that z equals lambda delta t is a complex number. Now, if you don't like it being a complex number, then just make it a real number. Make lambda some negative number so that our system's stable, and choose a delta t. Nothing really changes, but I want to do this in general. And so what we're going to see is that in the complex plane, this is C, the complex plane, and z is some variable in the complex plane, right? Z is in the complex plane. There's a unit circle around -1. And this is the only region where forward Euler is stable. So this is the only stable region. And so I'm just going to shade this. Everything else in the complex plane would make forward Euler unstable. Okay, so everything else here is unstable. Okay? So this is bad. This is for the forward Euler case. I'm just going to quickly label this. Forward Euler. So there's only this very small circle where lambda delta t can exist where forward Euler is stable. And I would recommend that you actually try to derive that from this expression up here. It's really not quite, it's not so difficult. Just plug in a z here and find out what z has to equal for this unstable condition to be true. And you'll find that for anything outside the circle, it's unstable. Okay? Now let's do the exact same thing for backward Euler. Okay, so that's my complex plane. We're going to do the exact same thing for backward Euler. Still in the complex plane. I still have some number z in the complex plane. But now what I find is that there's a circle surrounding +1. And this is the only region where anything is unstable. Okay, this is the unstable region. And everything else is stable. Okay, so this is the backward Euler case. Let's just label that. And this is what we found when we simulated our spring mass damper system last time, was even in a parameter regime where we knew that the system was stable, right? I pull the mass back, I let it go, and it oscillates back and forth and eventually comes to rest. Even when we knew that our system was stable, we found that for lots of delta t's, our forward Euler scheme was actually unstable. It would blow up and the solution went to infinity. whereas our backward Euler scheme became much more stable. It was stable for more delta t's. And these expressions here are exactly how you see that, okay? So I find this to be a very useful diagram, and you can certainly go from these expressions to these regions in the complex plane, and I would urge you to do so, okay? Excuse me. All right, so the last point here, we started with this really simple example where y dot equals lambda y. And now what I would like to do is relax the relax the condition that I'm only dealing with a single number y. And let's say that now I have a matrix system of equations. So y is a vector again. Y dot equals matrix A times vector y. Okay, not much has changed. This is example 2. And now we're stable if all eigs of A inside unit circle. This is a fact you'll learn when you take a course on ordinary differential equations coupled with a course on linear algebra. For now, you can take my word. This is very important, but kind of outside of the scope for now. And so all we have to change is very little. Our forward Euler and backward Euler schemes are actually very similar to what they are before. Here we have, instead of 1 plus delta t, lambda, we have identity matrix plus delta ta, not so bad. And here we have identity matrix minus delta ta, matrix inverse. Okay, this is exactly our forward Euler and backward Euler schemes. This is not terribly difficult. Okay. And so similar to what we had before when we were looking at stability, we say, okay, well, forward Euler, yeah, right? We have a trajectory. We have a trajectory y0 to y1 to dot, dot, dot to yn. And we're going to say yn equals this matrix to the nth power times y0. I plus delta ta to the n y0. Okay? And this is stable exactly when all of the eigenvalues of this are inside the unit circle. Stable when all eigs of I plus delta ta have magnitude less than 1. This is another way of saying the magnitude of all of the eigenvalues of this are less than 1. That just means that their length is less than 1 in the complex plane, and they're in the unit circle. Okay? So very little changed between a single equation, y dot equals lambda y, and a matrix equation. We're going to do the same thing for backward Euler. This is kind of an important result for the future. Let's take a step back. Most systems that we're interested in dealing with are not linear. We're not going to be integrating a lot of linear differential equations. We'll do a few. Most of them are not linear. But this is a tool that gives us kind of a flavor for the stability of these methods. And we can, if forward Euler is really bad even for a linear system and backward Euler is better, then maybe the same thing is true for nonlinear systems, although that's not guaranteed. Okay? So similarly, backward Euler, we have a chain of trajectories dot, dot, dot to yn. And here we have yn equals, I believe it's I minus delta ta to the power negative n times y naught. Let's make sure I'm right. Good. Okay, and this is stable. Let's say it's stable if and only if. That's an if with two f's. The eigenvalues of I minus delta TA inverse have magnitude less than 1 in the complex plane. Okay? And what you can do is you can actually break up each of the eigenvalues of this separately and plot them in the complex plane just like we did over here to get a flavor for the stability. So really, it's a very similar story. Okay, great. So for the last few minutes of lecture, I'm just going to derive a simple physical system. So I really love having motivations of why ordinary differential equations are important. And there's so many it's easy to choose from. Or rather, maybe it's difficult to choose from. It's easy to find one, but there's so many good ones it's hard to pick. So what I'm going to tell you about is a really nice classical physics example, the single pendulum. Okay, I'm just going to get my notes because I don't want to make any mistakes. So I think I've convinced you that forward Euler and backward Euler are simple enough that we can analyze them. We can look at the error properties and the stability. But honestly, neither of them were very good, right? The error for Euler was pretty poor. And at least for forward Euler, its stability properties were poor. So that's probably all I'm going to say about Euler for now. We're really going to start focusing on the next generation of better integrators. But for now, I just want to bring up an example and kind of code it up in MATLAB. Okay? So we have the single pendulum. Okay, just let's be explicit. Okay, I have a mass on a length, and it can pivot with angle theta. The mass is being pulled down by gravity. Okay, now you don't need to know Lagrangian mechanics or Hamiltonian mechanics to solve this, but it happens to be a lot easier if you do. So I'm just going to write down that my kinetic energy is equal to 1/2 m times my length times theta dot squared. My potential energy is equal to length times mass times gravity times 1 minus cos theta. And so I have a Lagrangian T minus V. This Lagrangian is probably one of the coolest things in all of mechanics. Essentially, all physical systems, in fact, quantum mechanical, relativistic, or classical, satisfy what's known as the variational principle of Lagrange that says that objects take the path of least resistance, basically. They minimize the transfer of kinetic energy to potential energy and vice versa in some kind of an integrated sense. This is really great equations. But what we really want out is a differential equation. This is the so-called Euler-Lagrange equations. Okay? And if we plug in our T and our V and our L, what we get is a very nice, simple differential equation. Theta double dot equals G over L sine theta. Nice, okay? But this is a second order differential equation, and we're looking for something that's a system of first order differential equations. So, any thoughts on how I can handle this? Okay, well, what I can do is I can suspend this into a system of two variables. I can say, well, x dot, okay, so I'm really going to call these x's because I don't want to type in a bunch of thetas in MATLAB. I'm going to say x dot equals v, and v dot equals g over L sine x. Okay? Now notice this is not linear anymore because this is a nonlinear function of my state variable. But we can still write this as d dt of a vector xv equals some function of xv and some other function of xv. Okay, this is what I mean when I say f of y or f of x. Okay, so that's the setup. Let's see if we have time to code this up in MATLAB. I think we have a few minutes, so I'm just going to go quickly, and you can kind of review this at your leisure. So what I'm going to do is I'm going to create a vector field for a pendulum. I'm going to say function dy equals pend of time, a vector y, gravity, length, and d. Oh, maybe I want some damping. Okay, I'm going to add d for damping. And then dy is, so x dot is v, and v dot is g over L times sine of x, which is my first variable in this vector y, minus damping times v. Okay? Notice dy is a vector with two elements. The first element is x dot, and the second element is v dot. Okay, that's all we've done. Going to save that here as pendulum. Okay, and then I'm going to create a function called sim pendulum where we simulate this. And I'm going to simulate this using a better integration scheme than Euler called Runge-Kutta fourth order, which we're going to derive in the next lecture. Okay, so I'm going to clear all. I'm going to say t equals a vector 0 to 0.1 to 50. So I'm integrating from time 0 to time 50 in increments of 0.1. So how many time steps is that? That's right, it's 501 instances of time, and it's going to take 500 time steps. I'll start with an initial condition of pi fourths and 0. So I have my pendulum at 45 degrees, 0 velocity, and I'm going to let it go. Gravity is about minus 10. Length is about 10. That's a pretty big pendulum. D equals 0.1. I'm going to have a little bit of damping because of friction. And then this is where I integrate my vector field. I'm going to say t comma y. This is the output of my function, time and my trajectory, is equal to ODE 45. This is a built-in MATLAB integrator that's much better than Euler. Okay, now it takes in some vector field, some time span, which I've already defined as t up here, and my initial condition. And for this vector field, I've defined a function called pendulum. So let's just remember that dy equals pend t comma y comma g comma L comma d. That's the that's the syntax I use for pendulum. So the vector field I'm going to integrate is at t comma y. I'm using function handles to create a function just of time and y, which is pendulum evaluated at t comma y comma g comma L comma d. Okay, so what I've done here is I've defined g, L, and d, and I've locked those into place in my pendulum function, and all that can vary is time and space. Okay, and that's it. This should integrate if I didn't make any errors, and then I'm just going to make a figure and plot time with my position, the theta, right, the first vector in y. I'm going to make another figure, and I'm going to plot my position against my velocity. And then I'll make a third figure and make a three-dimensional plot of time against y. Okay, so I should save this. Hopefully I didn't make any errors. And if I run it, I certainly seem to have made an error. Let's call my initial condition y0. See, undefined function or variable y0. Okay, and it's running, and I have trajectories. Okay, so as we expect, the first one, this is just theta, right? Theta starts off at 45 degrees. It swings, overshoots, swings back, but eventually goes to rest at 0. We see the same thing in our position of theta versus its velocity. And then this is the same plot in time. Okay, so I hope this all made sense. Next time, we're actually going to derive the Euler integration scheme that we used here, right? So ODE 45 is this better integrator that I haven't told you about, and we're going to start deriving this better class of integrators in the next lecture. Okay, thank you.